So welcome to MathStat 341, probability. We've been, of course, talking about only good things before the recording started today. And today will be lecture 19. And what I want to talk about today is going into a little bit more detail about differentiating identities. So we'd already seen a little bit of differentiating identities. We've done, and I want to talk today about Gaussian, exponential, negative binomial. And I want to continue a theme from earlier in the semester, namely the power of being able to tell a story. So you have a lot of very difficult calculations to do, but if you look at them just the right way, all of a sudden it simplifies and you can write down the answer immediately. Now, when you're doing something called differentiating identities, what do you think you need as an input? Identities. Yeah, you've got a 50-50 choice, with two words, right? You need identity. So how do we get identities? That's where a lot of the work is done. But once you have the identity, then we can proceed. One of the big things to be aware about is that you have to justify when you can switch orders. For the most part, I'm going to just pretend I have my physics or even better, my engineering hat on, and I don't even have to worry because I know my mathematician friends can justify it. Or I could even put my econ hat on and not even know that I have to justify it. Okay, but you have to, if you're going to go on in mathematics, you have to be able to justify that this can be done, that this is legal. This is why we have classes on real analysis. Right. So the big ones I want to do today, what's the first distribution? Normal, Gaussian, bell curve, anything that has this many names is important. Okay. When you look at this, it's screaming at you, I have mean, mu, and variance sigma. Otherwise, this is really bad choice of notation. But as is right behind the board over here, there was bad notation on this one when we came in. Bad notation often happens. What is 1 over cosine? Which bothers me. Right? Cosine should be linked with cosecant, sine should be linked with secant. The second one, there's two versions, is the exponential. I pulled these images from Wikipedia. I actually prefer this one. That's the one I like, because when you look at this one, then beta, the parameter, is actually the mean. In the second one, lambda is the reciprocal of the mean. And I much prefer to have my parameter be the mean. All right, the next one we talked about last time, this is the geometric. And if you remember the previous slide when we said we're going to do the Gaussian, exponential, geometric, and negative binomial, pretty clear that this one over here is going to be the negative binomial. And we're going to analyze it two different ways. We're going to analyze it directly, and we're going to analyze it by trying to write it in terms of simpler random variables. Right. Did we prove, we proved the normalization constant of the Gaussian, right? We did the polar coordinates trick. Did we prove that the integral from negative infinity to infinity of 1 over the square root of 2 pi e to the negative x squared over 2 dx equals 1? Did we prove this? Okay, then we will prove this. So let's let this integral be I. So I'm going to write I squared e to the negative x squared over 2 dx. And I can't use the same variable, so I'm going to use y for the second one, e to the negative y squared over 2 dy. I'm doing the standard normal here. You need to be comfortable converting from the standard normal to a non-standard normal and back and forth. So this means we only have to understand one particular instance to be okay. And again, it just comes from rescaling variables. I can send x to x over sigma. I can send x to x plus mu. So translations and rescales. So it's enough to just do this case. Well, this is the same as the integral. X goes from minus infinity to infinity. Y goes from minus infinity to infinity. 1 over 2 pi e to the negative x squared plus y squared over 2 dy dx. Now, when we do multivariable calculus, and this is one of the few times all semester we're actually going to use it, we don't have many techniques in multivariable calculus that are different from the techniques in real analysis. The big ones we have is we have change of variables, and we have shifting the order of integration, interchanging the order of integration. Well, given the remarkable symmetry up the wazoo that this one has, shifting, and switching the order of integration, that does nothing. So the only thing that's left is changing variables. So we have a function that only depends on x squared plus y squared. it should be screaming at you right now which variables to use. What does this remind you of? Circle, polar. So x is r cosine theta, y is r sine theta, x squared plus y squared is r squared, and then dx dy becomes r dr d theta, or a better way of viewing it, it's dr times r d theta. And the reason I like writing it as r d theta is the theta has no length. Dx dy, think of it as in meters squared. Dr d theta is just in meters. But r times the change in angle is going to give you an arc length. And that will be a meter squared as well. So if I put this into polar coordinates, I now have the integral 1 over 2 pi e to the negative r squared over 2 r dr d theta. Theta goes from 0 to 2 pi. R goes from 0 to infinity. Well, the theta integral is not so bad because there's no theta dependence. So what does the theta integral give me? Just 2 pi, and I'm dividing by 2 pi. It's almost as if I knew what the answer was when I wrote a 1 over square root of 2 pi outside, right? So we get 2 pi over 2 pi, integral r goes from 0 to infinity, e to the negative r squared over 2 r dr d theta. Boy, do we live life well. You know, if you want to do a change of variables, if you want to do a u substitution, you know, let u equal r squared over 2, and then du is going to be r dr. As r goes from 0 to infinity, u goes from 0 to infinity. So this just becomes the integral u goes from 0 to infinity, e to the minus u du, which is just e to the minus u. The minus sign flips the order of integration when we evaluate, and we just get 1. Did I make a mistake? The d theta should not be there. Yes, thank you. And so this is a truly strange problem. The way we evaluated the one-dimensional integral was we actually converted it to 2 dimensions. Because then we had the ability to use techniques from multivariable calculus. And so this proves that the normalization constant of the Gaussian is 1 over square root of 2 pi, at least for the standard normal. Okay, any questions on this calculation? So with a little bit of work, you know, rescale, we will get that the integral from minus infinity to infinity, 1 over square root of 2 pi sigma squared, e to the negative x squared over 2 sigma squared dx equals 1. So this is just the normal, still would mean 0, but now we're allowing the standard deviation to be sigma. And if we want to calculate the mean, is it easy or hard to calculate the mean of this random variable? What do you think? It looks hard, but you know, I'm still recovering from, you know, last class and running into the wall. So I want to take it a little bit easy on myself today. I'm only going to do easy integration. I claim this is an easy integral. We could do by parts, but there's an even easier way to do this integral. I don't want to integrate. I just want to look at it and see the answer. This is the mean of the Gaussian. What should the mean be? 0. So now that you know that it's 0, justify why it's 0. No. What can you say about the integrand? What can you say about this function? What kind of function is it? Symmetric. What kind of symmetric function? So there's 2 types of symmetric functions. If f of x equals f of negative x, you're even. If f of x equals negative f of negative x, you're odd. Got a 50-50 chance. It's odd. Right? E to the negative x squared. The Gaussian part depends on x squared, so that part's going to be even. How many of you have seen the Seinfeld episode, The Opposite? Where George realizes that every mistake in his life is due to the fact that he has no idea what to do, and his friends convince him to do the opposite. That only works in a binary situation where there's only two choices. As a Red Sox fan, I love the scene where he starts basically mouthing off to the owner of the New York Yankees. So this is an odd function. So if you think about what's going on, I have an odd function. It doesn't look like this, but here's an odd function, symmetric about the interval. And because things are decaying, sufficiently rapidly, again, this isn't it, the integral is 0. So the expected value of x is just going to be 0. And in fact, you can similarly show that all of the odd moments are going to be 0 for the Gaussian. So the difficulty is going to be the even moments. So we need to at least calculate the second moment to get the variance. So the expected value of x squared would be the integral from -infinity to infinity of x 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx. So these calculations, I believe, are all in the book. X squared, thank you. Now, if we want to try to do this, integration by parts is a great thing to try. So we want to have a u dv du v, and then the integral will be uv at -infinity infinity minus the integral from -infinity to infinity of v du. We have to figure out what to take for u and dv. It's okay if it's one, yeah. Okay, so u is perfect. So one thing would be to try u equals x squared. If we try u equals x squared, dv would be e to the negative x squared. We can't integrate that. So that wouldn't work. We could then try, well, let's make u e to the negative x squared. Its derivative is going to go to bring down an extra power of x. It's not going to help. So the best way to do it is to actually split. Let u equal x. dv is going to be, I'm not going to bother writing the 1 over 2 pi sigma squared. I'm going to just factor that out. Is going to be e to the negative x squared over 2 sigma squared x dx. du is dx. And then v is e to the negative x squared over 2 sigma squared. Now, the derivative of x squared over 2 sigma squared is I need a negative to come down. It's going to be negative x over sigma squared. So I need to divide this by sigma squared and multiply by sigma squared. And so I'll have a sigma squared coming up like that. When I look at the boundary term, uv at infinity, you can see that while u is getting large, v is getting extremely small, so the boundary term vanishes. So the expected value of x squared is going to be the uv at -infinity infinity, which is just going to go to 0. And then, whoops, I forgot the minus sign over here. And then that minus and the minus the integration by parts we reinforce, and we'll get a plus 1 over square root of 2 pi sigma squared coming out, integral from -infinity to infinity, e to the negative x squared over 2 sigma squared dx. But maybe I shouldn't have brought that outside. What is that integral equal to? 1. So this is just 1. So this is just equal to sigma squared, justifying the use of sigma squared as the notation. We can now calculate the expected value of x to the 2k by induction. Okay. So you can go through, and what you'll find is it equals 2k minus 1 double factorial. It's a nice calculation to do. Has anybody seen the double factorial before? Okay. If you raise your hand if you've never seen the double factorial. Okay. If you hadn't seen the double factorial, you would guess it's the factorial of the factorial. It's not, it's every other. So this means we have done this. Okay, good. Ah, yes, that's right. That's right. That's right. That's right. Yeah.
Don't give everyone
Just 1 second. I feel like doing the scene from Spaceballs when they're back from the nose operation. All right, so what we want to do now is we want to talk about how to find these without doing integration. And so we're going to use differentiating identities. So we need something that has a parameter that we can differentiate. So we want to calculate the expected value of, say, x to the 2k when x is a normal with mean 0 and variance 1. So we want the integral from -∞ to infinity of x to the 2k 1 over square root of 2 pi e to the negative x squared over 2 dx. Now, when I look at this, I don't really have an identity that comes to mind that I can differentiate, right? We need an identity to differentiate. So what we're going to do is we're going to start with the integral from -∞ to infinity of 1 over square root of 2 pi e to the negative x squared over 2 dx. What should this equal? Not 1. Sorry. It does equal 1 because I didn't write it properly. E to the negative x squared over 2 sigma squared. What should it equal? Not sigma squared. Sigma, because the sigma squared is underneath the square root, right? You can also do a unit analysis. The exponential has to be unitless, so x and sigma have to have the same units, same meters. Dx is going to be in meters, so this whole integral is in meters, so it has to be something like sigma. So without even doing any calculation, I know it's going to be something like sigma and not sigma squared, just by unit analysis. Now I have an identity that I can differentiate. And then what I can do is I can differentiate, and then I can set sigma equal to 1, and then I will have the distribution that I want. So what I'm doing is I'm putting, even if I only care about the standard normal, it's actually better to look at a family of normal distributions because I have the flexibility of a parameter I can differentiate with respect to that. So what I'm going to do is I will apply sigma d by d sigma to both sides. And what is the derivative of the integral? The derivative of the integral is the, not quite. What do I want to do with the differentiation and integration? So right now I first integrate and then I take the derivative rather than, I want, what? No. I have two operations. I have the integration operation, which I do first, and then I'm going to do the differentiation. Rather than doing integration first and then differentiation, I want to say this is the same as differentiating first and then integrating. And this is where you need real analysis. You need to be able to justify switching the orders. And if we can do that, we then get the integral from -∞ to infinity, x to the 2k, and then 1 over square root of 2 pi. And now we take the derivative with respect to sigma of e to the negative x squared over 2 sigma squared. Oops. Dx. And what's the derivative of sigma with respect to sigma multiplied by sigma? What does the right-hand side equal? It's just sigma. Okay. Now, what's the derivative of e to the negative x squared over 2 sigma squared with respect to sigma? So I'm going to have, this is, I get back the exponential, And then this is e to the negative x squared over 2 times sigma to the negative 2. So we'll get negative 2, negative x squared over 2, sigma to the negative 3. So it's going to be integral from minus infinity to infinity. Oh, sorry, there's no x to the 2k here. Sorry. My apologies. Because we're starting off with this identity. And so we're applying d by d sigma to this identity. So now when we take the derivative, what is the derivative of e to the negative x squared over 2 sigma squared? That's negative x squared over 2. And we have a sigma to the negative 2 that becomes a negative 2 over sigma cubed. Then we have a 1 over square root of 2 pi. And then we have e to the negative x squared over 2 sigma squared dx. And this is just equal to sigma. Well, the negative 2 reinforces with the negative sign up here and becomes a 2, cancels with a 2 down here. We have a sigma cubed, right? If I'm integrating, I want to have a square root of 2 pi sigma squared. So what I want to do is I want to take one of the sigmas and put it in there. I'm trying to say. Oh, I've also got a sigma over here. It's sigma d by d sigma. Right? I have a sigma d by d sigma. I forgot to include sigma. So I've got sigma cubed sigma over here. That's a 1 over sigma squared. One of the sigmas comes in here and makes it a square root of 2 pi sigma squared. The other sigma comes over to the other side and gives me a sigma squared. And so when you just move the algebra around, you'll get sigma squared is the integral from minus infinity to infinity of x squared e to the negative squared over 2 sigma squared, 1 over square root of 2 pi sigma squared dx. And there's the formula for the second moment. Is we just applied sigma d by d sigma. And when we did that, it brought down an x squared. If we were to do it again, we would bring down another x squared and we can get the fourth one. And so we don't have to be clever and figure out that we should do the integration by parts by actually splitting up the x squared as x times x and putting one of the x's in. All right, so I hope this is giving you some sense of the power of differentiating identities. All right, what I want to do now is the exponential. And so we'll let x be exponential with parameter lambda means the probability is 0 if x is negative and 1 over lambda times e to the negative x over lambda if x is greater than equal to 0. So to calculate the mean, we need to integrate from 0 to infinity of x times 1 over lambda e to the negative x over lambda dx. How would you do this integral? By parts. And so you could integrate by parts. Here's another way. We start with the identity that the integral from 0 to infinity of 1 over lambda e to the negative x over lambda dx equals 1, or the integral from 0 to infinity of e to the negative x over lambda dx equals lambda. So this is our identity. What do you think we want to apply? What operator? I'm sorry? So one is d by d lambda, but I might want to do something a little bit of a twist to it. Yeah, lambda d by d lambda. And we've done this before. And when we put this extra lambda, it keeps the powers nice. And so when we do this, it yields, lambda d by d lambda of lambda is equal to lambda d by d lambda of the integral from 0 to infinity e to the negative x over lambda dx. Now, what is true about the derivative of the integral? It's the integral of the derivative. We don't always have to justify that, but if we have that, we then get 1 equals, lambda integral from 0 to infinity d by d lambda of e to the negative x over lambda dx. Well, that's just lambda integral from 0 to infinity. Now we have e to the negative x lambda, so it's e to the negative x lambda to the negative 1. So I'm going to get a negative x, and then the derivative of lambda to the negative 1 is going to be negative 1 over lambda squared e to the negative x over lambda dx. Well, my density is 1 over lambda e to the negative x over lambda. I have an extra lambda over here, so I want to bring that lambda over to the other side. And so when we bring it over to the other side, wait, this should have been the lambda. Okay, because we were applying lambda d by d lambda to lambda. So we then get lambda. Well, actually, there's no need to bring it over to the other side because I've got a 1 over lambda squared, but I have a lambda outside over here. Lambda divided by lambda squared is 1 over lambda, which is exactly the density we need. So we get lambda equals the integral from 0 to infinity of x 1 over lambda e to the negative x over lambda dx, which is the expected value. So we were able to calculate the expected value without any trouble. Could we calculate the variance? Yeah. Do people want to do the variance? Just do another. Sure, let's do it. All right. So we know that the expected value of x is lambda. The variance of x is going to be the expected value of x squared minus the square of the expected value. So we just have to calculate the expected value of x squared. From what we just did a moment ago, we have lambda was equal to x 1 over lambda e to the negative x over lambda. So we have lambda equals the integral from 0 to infinity of x 1 over lambda e to the negative x over lambda dx. I could apply lambda d by d lambda again. Why am I not thrilled about differentiating right now? What would I have to use on the right-hand side? So I want to take the derivative with respect to lambda, but what do I have to use on the right-hand side? Sorry? No. My function as a function of lambda is 1 over lambda e to the negative x over lambda. What differentiation rule do we use to take that? No, we're just taking derivatives. We're not integrating derivatives. Right. If I want to take the derivative, what do I need to use to take the derivative of 1 over lambda product rule? I don't want to use the product rule. Well, for those of you who are following Central, I don't want to be a pirate. So what I'm going to do is I'm going to move a lambda over to the other side. I actually think I do have a puffy shirt or something that's a close approximation. So if I move the lambda over to the other side, first I get lambda squared is the integral from 0 to infinity of x e to the negative x over lambda dx. Isn't this much nicer now? I had to take the derivative of the left-hand side anyway. It already had a lambda. Having another lambda there doesn't really make it that much harder. Lambda and lambda squared are very similar difficulty. But now the right-hand side is no longer a product rule. So we apply lambda d by d lambda. And so we have lambda d by d lambda of lambda squared is equal to the integral from 0 to infinity of x lambda d by d lambda e to the negative x over lambda dx, as the derivative of the integral is the integral of the derivative. Okay, so the derivative of lambda squared is just come on, you got to answer this fast. I mean, my son's in pre-calculus and he knows this. Of course, he's also in calculus. But that's it. So we get 2 lambda squared. And then on the right side, what do we get? Well, we have our lambda, we have our x, and we just saw a moment ago that the derivative of e to the negative x over lambda is negative x over lambda squared. So we get negative x times negative 1 over lambda squared, so it's just x over lambda squared. So we just get x over lambda squared e to the negative x over lambda dx. Well, everything is working out beautifully. I want to have a 1 over lambda. I have a 1 over lambda. So this is going to just be the integral from 0 to infinity of x squared 1 over lambda e to the negative x over lambda dx. That's the second moment. So the second moment is 2 lambda squared. So the variance is equal to 2 lambda squared minus lambda squared, which is just lambda squared. So what is the standard deviation? Which also equals the mean. So here, the mean and the variance, the mean and the standard deviation are both equal to the same parameter lambda. If you want, you could view lambda then as the standard deviation and not the mean. I don't look at it that way when I have negative x over lambda, but okay. But maybe it is better to view it as the standard deviation because I'm telling you how I'm normalizing it. All right, so the next one is the geometric random variable. And we're going to say x takes on values from 0, 1, 2, ... And then the probability is 1 minus p times p to the n. So p is the probability of a failure. 1 minus p is the probability of success. It bothers me a little bit that p is the probability of a failure. Yeah, I like to think of things more positively, but it's just more convenient when we're doing our geometric series to be looking at it like this. Why is this useful? Well, what we're trying to do is we are trying to calculate quantities like mean and whatnot. So we start with the sum n goes from 0 to infinity of 1 minus p times p to the n equals 1. Or the sum n goes from 0 to infinity of p to the n is 1 over 1 minus p. That's really what we're starting with. We're starting with the geometric series and we're just normalizing it. So what you can view this is how many times do I have to toss a coin with probability p of failure before I have my first success? So x is the number of tosses before, let me see, no, it's not the number of tosses, it's the number of failures before the first success. What's the smallest number of failures we could have? 0. And what's the difference between the number of failures before the first success and the number of tosses before the first success? Yeah, tosses equals failures plus 1. So if I understand x, I understand x plus 1. All right, so what we want to do is we want to calculate the expected value of x, which is going to just be the sum, n goes from 0 to infinity of n times 1 minus p, p to the n. And what we're going to do is we apply p d by dp to the sum and goes from 0 to infinity of p to the n equals 1 minus p inverse. This is going to be the identity that we start with. And over here, this is going to be the operator that we apply. If you think about this, this is very similar to all the calculations we've been doing before. We start off with the fact that it's a probability distribution, so something either integrates or sums to 1. And so in order to have something that we can differentiate, we take part of it and move it to the side of 1, so that when we differentiate, we just don't get it. You could, of course, keep it on the same side and then use the product rule. If you want to do more algebra or more calculus, more power to you. I prefer to minimize how many calculations I have to do, because the more calculations I do, the greater chance of an error. All right, so if we apply this, we then get p d by dp of 1 minus p. So we'll get p times negative 1 minus p to the negative 2 equals the sum and goes from 0 to infinity, and we'll get p times n p to the n minus 1. So we get oh, there's one mistake I made. When we take the derivative on the left-hand side, when we take the derivative of 1 minus p inverse, it's negative 1 minus p to the negative 1, and then the derivative of 1 minus p. What's the derivative of 1 minus p? Negative 1. And so it's going to be an extra negative 1. All right, so when we combine everything, we get p over 1 minus p squared equals the sum and goes from 0 to infinity of n times p to the n. But we don't want n times p to the n. We want n times 1 minus p to the n. So I have to move one of the 1 minus p's over. And from this, we get p over 1 minus p is the sum and goes from 0 to infinity of n 1 minus p to the n, which is just the expected value of x. And so we've calculated the mean of a geometric random variable. So one way you could look at this is I have a bunch of boxes, and each box has probability 1 minus p of having the toy that I want. How many boxes do I need to open before I get the toy that I want? So there's a lot of problems in the real world that can be modeled like this, where you're waiting for the first thing to happen. However, instead of waiting for the first success, what might you be waiting for? The second, or the third, or the fourth. And then maybe a success is a bolt of lightning hits. And then if you have too many bolts of lightning that hit, then the structure is weakened and is destroyed. And so how long can you last until things collapse? How many hits can you take? So what we want to do now is we want to study the negative binomial. So this is the last one. And so what I'm going to do is I will just put the negative binomial over here. So negative binomial. Does this seem similar to the geometric that we looked at a moment ago? It looks a lot like the cookie problem. So the geometric was the density 1 minus p we did it to the first power, and then we had p to the n. So here, unfortunately, the way this is being done is it's a slightly different notation. And so here we are having k be the parameter that we're looking at. K is going to go from 0 to infinity. And so it's flipping the roles of p and k. And so what I would like to do is I'm going to just change it. So I want the probability that x equals n. And what I'm going to do is I'm going to replace p with 1 minus p. So I'm going to have 1 minus p to the k, p to the n. And so what I'm going to be doing is I'm going to have R equals N. No, I'm going to have R equals K. And I'm going to have K equals N. So K plus R is going to be N plus K minus 1. And then R minus 1 is going to be K minus 1. Like the cookie problem. So no, because what I want to have is I want to have K successes. And so this is what I truly hate this. Because everybody uses different notation. Are you counting successes or failures? What's P? What's 1 minus P? And so we're going to use this one. Notice that the geometric is just the case K equals 1. Because then the binomial coefficient N plus K minus 1 choose K minus 1 just becomes N choose 0, which is just 1. And then 1 minus P to the first power, it just reduces. So this is really, you could view this as the sum of K geometric random variables. So let x1 dot 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 xk be IIDRV, independent identically distributed random variables that will be geometric with parameter P. Then X is just X1 plus XK. So the negative binomial is actually just the sum of K geometrics. The way you can view this is I wait and wait and wait until I have my first success. Then I wait and wait and wait and wait and wait until I have my second success. Then I wait and wait and wait and wait until I have my third success. And if I want to know how many total failures were there, well, I just count how many failures were there before the first success, plus how many failures were there between the first and second successes, and so on and so on. So what's the expected value of X? So I have X is X1 plus dot 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 plus XK. How would I find the expected value of X? Yeah, so the expected value of the sum is the sum of the expected values. Which is just going to be K times P over 1 minus P. So I don't have to do the terrible difficult calculation. Now the question is, why is this the right definition? So here we're saying, the probability that X equals N is going to be N plus K minus 1 choose K minus 1, 1 minus P to the K, P to the N. So if we think about what's going on, we have K successes, we have N failures. What do you know must be the case of the very last toss? It has to be a success. And now over here, we have K minus 1 successes. We have N failures. And any of those strings is equally likely. How many spots are there? How many ways are there to choose which of the boxes get a success? No, it's easier than cookies. We have N plus K minus 1 boxes. Choose K minus 1 to be successes. How many ways can we do that? Yeah. So it's going to just be N plus 1. I'm sorry, N plus K minus 1, choose K minus 1. And then for each of them, I have a total of K successes. So that's going to give me a probability of 1 minus P to the K. And I have N failures, that's P to the N. So that's where this comes from. So now that we know that, we know that the sum, N goes from 0 to infinity, of N plus K minus 1, choose K minus 1, 1 minus P to the k times p to the n equals 1. It is not immediately clear when you look at that sum that this sum is equal to 1. But because we have an intuition on this, because we know that this is supposed to be a probability distribution, it has to sum to 1. So what we do now is we move the 1 minus p to the other side. So we have a sum and it goes from 0 to infinity, n plus k minus 1, choose k minus 1, p to the n is equal to 1 minus p to the negative k. And now let's apply p d by dp to both sides. And again, this is the technique we always do. This is the 4th time today. Anything you do this many times is a technique now, okay? We move part of it over to the other side so we can differentiate. So when we apply p d by dp, we get the sum, n goes from 0 to infinity, of n plus k minus 1, choose k minus 1. The n comes down, and it still stays as a p to the n because we multiplied by p. On the other side, we now take the derivative, and we get negative k, 1 minus p to the negative k minus 1, and then we get a negative 1 from the derivative. Okay, well, we know that we want this to be the mean. So for this to be the mean, I have to remove the 1 minus p to the negative k and bring that over to the other side. And so when I do that, I get the sum, n goes from 0 to infinity, of n plus k minus 1, choose k minus 1, 1 minus p to the k, p to the n, equals k, and I'm left with a 1 over p in the denominator. And there was, I forgot, I applied p d by dp, that's why I have a p over here as well, or just k, p over 1 minus p, and this is just the expected value of x. And so we actually calculated the mean of the expected value. We handled this horrendous sum without doing any summation, just by taking derivatives and moving things around. And we even have extra time left in the class so I can pontificate. I mean, this is wonderful, right? We finished before 9:50. This is one of the most powerful methods I know. We've just seen it applied successfully in 4 different cases. You want any moment, I can just punch my way through it. All right, have a great weekend.